Could you use a microphone, please?
Better?
Thank you.
Okay, great. So one thing I really want to start to address today are why are trees so important, okay, in these questions. Okay, and so somehow the last thing I'll get to in my talk is a pair of results by Weitz and Sly. And the punchline of these pair of results is that a certain computational threshold coincides with the physical phase transition. And that's where we'll get to by the end. But really, I want this to be introductory, and so please do interrupt me as I go and ask questions. I purposely wrote with my usual handwriting, so you have to ask questions as the talk goes on. That's intentional. Okay, so spin models on graphs. So we're going to talk about random processes on graphs, actually just as in the previous talk. And one key model that we'll talk about is the Ising model. What's the Ising model? It's a very basic model of a magnetic material. But what is it mathematically? It's a probability distribution on assignments of +1 spins or -1 spins to the vertices of some finite graph. And how do you choose this probability distribution, or how do you specify it? You pick a particular assignment of spins with probability proportional to the exponential of beta, that's some constant, times the sum over all edges of your graph, sigma u, sigma v. So in particular, this counts the number of, you can think of them as agreeing edges minus disagreeing edges. Because if you're plus plus, you get a plus. If you're minus minus, you get a plus. But if you disagree, you get a minus. And then what you have to do to make this a probability distribution is you have to divide by this normalizing constant to make it a probability distribution. And this is the partition function of the model. And this will be a key object here. And the model, the Ising model, is ferromagnetic if beta is non-negative, which means that we prefer across edges to see the same spin. And this is, we actually already heard about the piles argument for the 2D Ising model earlier. The second model I want to focus on in this talk is the hardcore model. This is a toy model of a gas. It's somehow like a discrete version of something you'll hear about later in the week, the hard sphere model in Euclidean space. But what is this? This is the probability distribution on independent sets of a graph. So sets of vertices that induce no edge. And how do you pick this independent set? Well, you pick it with probably proportional to lambda to the size of the independent set. And so lambda is some parameter, the activity. And again, you divide by the partition function, which is the normalizing constant. In this case, the partition function in graph theory is just called the independence polynomial. And here, the larger lambda is, the more you prefer large independent sets in your probability distribution. Okay, and the classical statistical physics point of view is to study spin models like these on a lattice like ZD, let's say Z2 or Z3 if you want to be the most like the real world that you can be. And so what I want to briefly go over is, in this classical setting on ZD, what is the phase transition phenomenon and how do we define it mathematically? And so what's the phase transition phenomenon supposed to capture? It's supposed to capture, well, in the case of the Ising model, the spontaneous magnetization. If you run a current through some iron and make it a magnet, and then you take the current away, maybe it will stay being a magnet after you take it away. For the hardcore model, this is supposed to represent the freezing of a gas to a solid. Okay, so mathematically, how do we define this? The first way, and maybe this is the most complicated way, is in terms of infinite volume Gibbs measures. And so I want to take a little time, because if we're going to talk about spin models on trees, this is an important point. So ZD is an infinite graph. And so the definition I just gave you of the Ising model or the hardcore model doesn't apply. You can't define this model that way on an infinite graph. So how do you define the Ising model on ZD? Well, one way is to say, let's say I fix my parameter beta. This is the specification of the model. Now I want to define a probability distribution on ±1 assignments to all the vertices of ZD. What makes this an Ising model infinite volume Gibbs measure? Well, what makes it a appropriate probability distribution is the following. We want to say, we want to fix some finite set, call it lambda, so that's this box here. And we want to look at some configuration of on the infinite graph of plus minus 1 spins. And we want to condition on what happens outside this box. And this induces some probability distribution inside the box, right? Just the conditional probability distribution. And what we want to insist is that this probability distribution induced by this conditioning on the infinite graph actually is the same as if I just looked at this finite box and fixed the spins that touch the box on the outside, and then did the definition I did before for a finite graph. So the conditional distribution should satisfy this finite volume Gibbs measure definition. And of course, that's like a bunch of equations, right? For every configuration, for every box, these conditional probability distributions have to satisfy this condition, and this is called the DLR equations, de Bruijn, Langford, Ruel. And so this is one way to say how can you construct or how can you define infinite volume spin model. And one thing that's nice is that in a lot of generality, such a Gibbs measure always exists for a given specification. So I pick my value of beta, I pick my infinite graph, let's say Z4 if you like, Z3. There will be an infinite volume easing model with this parameter beta. Or if I fix my value lambda, there will be an infinite volume hardcore measure. But the big question is there only one? Okay, and so we can ask for a given specification and a given infinite graph, is there a unique infinite volume Gibbs measure, or are there multiple infinite volume Gibbs measures? And then if we have a picture like this, that for beta small before some beta critical, you have only one Gibbs measure. And for beta bigger than beta critical, you have more than one, then we would say a phase transition occurs at beta critical. Okay, and so you can ask, how could you possibly construct such measures? For the easing model, at least, it's kind of easy to see how, if there's more than one Gibbs measure, you can construct them. What I could do is I could take some boxes, and then I could insist that on the boundary, I put all pluses all over the boundary. And then I could look at the finite volume Gibbs measure I get on my box, and then take the box bigger and bigger and bigger and bigger, look at the weak limit of these probability measures. Turns out that there has to exist, at least in a subsequence, an infinite volume Gibbs measure. And now somehow that is the one that most prefers plus. But then you could do the same thing with minus boundary conditions, and you could take that limit, and then you could ask, does this give you the same answer? Okay, for the easing model, because of like FKG inequality, exactly the point at which those two give you different measures is beta critical. For hardcore, does anyone have a guess? How do you put different boundary conditions on to get different measures? On Z2, let's say. Yeah, so on Z2 is a bipartite graph. This is going to be the theme of this lecture. So if you think about a very high density independent set, you can't share, can't have two occupied particles across an edge. There's two maximum independent sets, ground states, the all even, coordinates add up to even, or the all odd. And so you would think at large lambda, you're going to find independent sets that are mostly even or mostly odd. So what you can do to create two different Gibbs measures is put all even occupied boundary conditions or all odd occupied boundary conditions. A caveat, we don't know what I just said about like the point at which that gives you two measures is the critical point. We don't even know there's only one critical point for hardcore. So things can get complicated fast. Okay, so that's one definition of phase transition, uniqueness or non-uniqueness of infinite volume Gibbs measure. And of course, this really only makes sense for an infinite graph. Just like in the first talk, it's going to be a big distinction between infinite and finite graphs here. Okay, second definition, analyticity of the pressure or the free energy. And so I can define something called the pressure, which is the following. I look at, let's say, a sequence of boxes, lambda n, finite boxes in ZD. I look at the partition function, so z lambda n of my parameter lambda. Take a logarithm, that's typically going to be like order n, and then divide by the number of vertices. Let's say there's n vertices there. And then take a limit, and that gives me something. So it turns out when my graph is ZD, which has polynomial growth, boundary size is small, this limit, you can show this limit exists. But for the rest, for later in the talk, be careful. This limit need not exist if you have big boundary. But it exists, and in fact, it doesn't even depend on what boundary conditions you put on. You can put different boundary conditions on, and you'll always still get the same limit. Somehow, what you do on the boundary is minuscule compared to the size of the partition function. And so this function makes sense. And then we can ask, what does this function look like? And another definition of phase transition is a phase transition occurs at lambda critical or beta critical for easing if this function is not analytic at a certain point on the real line. And so if, for instance, if it had a discontinuity in its second derivative, that would mark a phase transition point. Now, analytic, right? Analytic refers to like complex analysis. And so somehow this is saying that phase transitions are related to the behavior of the partition function when you plug in complex values of the parameters. And I mean, this is a whole topic for a different talk, but this is the Yang-Lee theory of phase transition. So you have a phase transition if you have a sequence of complex zeros approaching the positive real axis. So this is that's a second definition. A third definition, and this is more probabilistic, is you can ask, for a sequence of graphs or even an infinite graph, let's look at the covariance between the spin value at vertex u and the spin value at vertex v. Does this decay in the distance between u and v, let's say uniformly over your sequence of graphs or in your infinite graph? And you can ask, does it decay exponentially fast in the distance? Does it decay polynomially fast? And so we can say there's a phase transition if you go from a parameter regime where you have exponential decay of correlations to not having exponential decay of correlations. That would be another definition of phase transition. Good, so those are the math definitions. Let me show you some pictures just to give an idea of what's happening. So here's a finite box of Z2, and I took two samples from the hardcore model. Actually, I put periodic boundary conditions, so it's a torus. And when I'm plotting here, it's Z2, so each little square is a vertex in Z2. The white squares are ones that don't have an occupied vertex. They're unoccupied. And then the colored squares have a vertex of the independent set. Okay, but I've colored them red or blue based on their parity. And what I want you to see on the left is here lambda is relatively low. Red and blue are kind of mixed all about. Okay, so you might say that's like disordered, if you like. It looks random, but you can see like locally it is respecting like this checkerboard pattern, right? You get little patches where you somehow align with the even or odd, but that doesn't globally persist in this big box. Where on the right here, I'm picking large lambda, and now it looks a lot different, right? It looks like globally we've agreed upon even, and then in little places we have some defects that are odd or missing. And if I ran this experiment again, so it's another topic to tell you how I got these simulations, but if I ran it again, you might see mostly red with some splotches of blue. Okay, but clearly it looks like something different is going on here. And you can imagine, for instance, like maybe correlations persist on the right, but not on the left. Knowing one square is blue on the right tells you a lot about whether a square far away might be, blue. Where on the left, it doesn't tell you much. Okay, so that's hardcore. Here's a picture for the easing model. So here is, I guess this is low beta and high beta. It's a little confusing from physics that low beta is high temperature and high beta is low temperature. But again, what do you see? So locally on the left, you see people want to agree with their neighbor, but globally there's no agreement and there's disorder. Where on the right, we've fixed on, say, plus with some deviations, with some little minus islands. And if I ran it again, I might very well get the opposite, mostly red with some blue islands. So that's ZD. And let me just say that it can be very challenging to understand phase transitions on ZD. For like Ising model, we understand things very well, but even for hardcore, there's many open questions. For Z2 hardcore, we don't know where the critical transition is, and we don't even know there's just one. But for Ising, it's pretty well understood. Just for historical purposes, let me say there's another model that's even harder to analyze. We know almost nothing about, and that's the Edwards-Anderson model. Let me just tell you what this is because it plays a key role in the history of a lot of stuff. Here you have plus minus 1 spins on Z2 or ZD, but the only difference is instead of putting a beta in front of the sum, you have a beta UV in front of the sigma U, sigma V for each edge. And this beta UV is a random variable. It's a Gaussian, let's say mean 0 and variance B. Okay, but it could be positive or negative. So just randomly on each edge, you may prefer to see the same spin or want to see different spins. And so you can't just like in the Ising model decide to have the most probability by all agreeing plus. And you can't like in the hardcore model say, well, I'm going to pick my even sublattice to be plus, my odd sublattice to be minus. I can't do either one. And so this is a disordered model. There's randomness in the definition of the model. And then what you want to do is pick your random variables, your betas, and then look at the Gibbs measure you get. And this is a model of a glass, like literally like the glass in a window. And it's very hard to understand. And this sort of motivated a lot of interesting mathematical work, physics work, and so on. Okay, so that's my brief introduction to the classical models. Any questions before I move on? Yeah. Yes. Yeah, so that's a great question. So you can look at any boundary conditions you want. In the uniqueness regime, right, beta less than beta critical, you'll always get the same answer, of course. But you could get many, it's not just that there's 2 measures in the non-uniqueness regime. There's like uncountably many measures, maybe. So you can get many crazy things. Maybe I think that's true. Like in particular, you can get like convex combinations of extremal measures. But it's a great question to ask, like putting plus and minus, because then you see some interface. So lots and lots of rich behavior by picking different boundary conditions. Other questions? Okay, so now I want to move on and talk about the same type of spin models, but now on trees, infinite trees, and random finite graphs. Okay, and we'll try to say, you know, do these definitions still make sense? If not, what can we do? And so the star role will be, I'll call it T delta, which is just the infinite delta regular tree. Okay. So I guess Tom didn't say, but it's easy to understand the percolation threshold on T delta, right? And so just as it's easy to understand, say, the percolation threshold on the infinite tree, you can also understand uniqueness, non-uniqueness thresholds for many spin models on the infinite tree just by doing like a recursive calculation. So let's say for the Ising model, you know that like plus and minus boundary conditions are sort of extreme. You can just see, like, do a recursion saying what's the marginal of the next guy if the last guys had this thing. You know, at first you fix all plus, and then you say, well, now they're independent with some marginals. What's my marginal? Do it again and again. And you can see when you get 2 different answers in the limit. Okay, so for hardcore, what I wrote was, so if we impose the all even boundary conditions, even depth from the root, or the all odd boundary conditions occupied at odd depth from the root, Then you look at the marginal. What's the probability that the root is occupied in this random independent set on a tree where you set the boundary conditions at a finite depth, so one way or another. And if you put even boundary conditions in, this is going to favor that the root is n, right? Because obviously if your neighbors are n, you can't be n. So how do you make your neighbors not be n? Well, you put your neighbors n as much as you can, and you keep going, switching back and forth. And so you can ask, do you get a different answer in the limit as the depth of this tree where you're setting the boundary conditions goes to infinity? And you can calculate exactly where this occurs. So let's call this lambda critical of delta, and it's some explicit function of delta minus 1 to the delta minus 1 over delta minus 2 to the delta. But think of this for like large delta, this is like E over delta. And you'll see this E later this week. And so what do we know on the tree? Well, there's a unique Gibbs measure if lambda is less than lambda critical, and actually correlations decay exponentially fast. And if lambda is greater than lambda critical, you have non-uniqueness. So for instance, you can get a different infinite volume Gibbs measure on the tree by taking the limit of even occupied or limit of odd occupied boundary conditions. And you don't have correlation decay. So in particular, if I set a bunch of vertices at depth L to be in and they're at even depth, that correlation will persist. So in that sense, that's quite nice. Notice that you can't use this analyticity definition of a phase transition here, because this the limit of 1 over n log partition function, there's tons of vertices on the boundary of a tree. So in particular, this limit could not exist, or it certainly could depend on the boundary condition. And so this definition really doesn't make sense. And so you can use the definition of uniqueness of infinite volume Gibbs measure. You can use the definition of correlation decay. But it's gonna be kind of critical exactly how you define correlation decay. So I'll leave this for Horace's talk later today to talk about different types of mixing. Okay, so the tree, in a sense, the tree is kind of nice. You can, for many spin models, not all, but many, you can fairly easily understand the phase transition, uniqueness, non-uniqueness phase transition by this recursion. But you lose a little bit, because maybe you're interested in something about finite graphs, okay? And so one question you could ask is, are there finite graphs that have some of the same nice properties with respect to spin models that the infinite tree has? And the answer is yes, but it's complicated. So let's get into that. And so first I want to, back to the history. I like history. Why would statistical physicists want to ask this question? Why do they want to understand a spin model on a finite graph that looks like a tree? And so one reason is trying to understand Edwards-Anderson model. Okay, so you have this Edwards-Anderson model of a glass. It's really, really hard to understand. The first thing you might do would be to say, let's study this on a simpler graph. Okay, what's the simplest graph there is? The complete graph. Okay, so well, maybe not the simplest, but almost the simplest, the complete graph. And you could study the Edwards-Anderson model and the complete graph. This is the SK model, the Sherrington-Kirkpatrick model. And that, Parisi came up with a formula for the limiting free energy. It was proved. But then you could say, well, I sort of lost a lot. I lost any notion of local geometry. Everyone's connected to everyone else. And so what the statistical physicists did was they said, let's study this model, the spin glass, so this one with random couplings, on something they call the beta lattice. Okay, so it's a lattice, but that looks like a tree. And what really is this? This is really like a random regular graph. So uniformly random delta regular graph on n vertices. Okay, and one of the properties of such a random graph is that it converges locally to the tree. So if you pick a vertex and look at its neighborhood, depth t neighborhood, with high probability this will look like the depth t neighborhood of the infinite delta regular tree. So this is Benjamini-Schramm convergence. In that sense, it converges to the tree. Okay, but now, okay, so now we can ask, let's take our favorite spin model and look at it on a random graph that's locally tree-like. What definitions of phase transition will work or not work? Okay, well, you can't use uniqueness, non-uniqueness, right? It's not an infinite graph. You can't set some boundary condition, or you can't, it really is a finite graph, and there's no way to keep extending it and extending it. But you can use this analyticity definition. And so you can define, let's say for hardcore, something that depends on delta. You can define this limit. So you look at the random partition function, so z of this random graph, take the logarithm. Now take the expectation of that, right? There's the randomness in the graph. So take the expectation, divide by n, and take the limit as n goes to infinity. Now, in a sense, it's like okay to use the expectation because it can be shown fairly generally that the log z has nice concentration properties. And it can also be shown that this limit exists. But important also for my talk tomorrow, this can be very different than if you take the log of the expectation of z. Okay, so it really matters that you're taking the expectation of log z. But this function is defined for many of these models, and then you can ask, is there a non-analytic point in this function? So that's a perfectly nice definition of a phase transition on a random graph. And then you can also ask about correlation decay on a typical realization of the random graph. So if you pick a random graph, then you can say, well, with high probability over the choice of that graph, do I have nice correlation decay properties? And that would be another definition. Okay, so we have this infinite tree where we understand the phase transition in the uniqueness, non-uniqueness sense. Now we have this model of a finite graph that looks like a tree locally. So we can say, is the uniqueness, non-uniqueness phase transition on the tree, is that reflected in the phase transition that happens on the random graph? Pretty good question. And the answer, again, is complicated. It may or may not be. Okay, so let's see both cases. So for the Ising model, so that's the first place to start. These two phase transitions do coincide. So exactly at the this beta critical for the Ising model, uniqueness, non-uniqueness on the tree. Below beta critical, you have analyticity of this random graph free energy, and you have exponential decay of correlations. And you even have more. You have, so Dembo Montanari showed you have something called local weak convergence. So this is like Benjamini-Schramm convergence, but you put the model on top of your graph, and then you say, what does like the annotated local neighborhood look like? And they showed that that converges to the unique Gibbs measure on the infinite tree. Okay, so that's great. That story is, that's really nice. And then if beta is greater than beta critical, then you have you don't have correlation decay in the Ising model in the random graph. You have phase coexistence, so sort of 50-50 chance of seeing mostly plus or mostly minus. And so there everything's nicely reflected. A little small note, a caveat already for the Potts model. So the 3 or more color generalization of Ising model, it's already much less clear. The phase transition on the random graph doesn't coincide with the uniqueness threshold on the tree. But we'll see it more for hardcore. So what happens in hardcore? So remember for hardcore, how did we get the phase transition on the infinite tree? We put either all odd occupied or all even occupied boundary conditions, and we said, does that change what happens at the root? Okay, now try to somehow like simulate this on the random graph. Okay, so what you want to say is like, you want every vertex to notice like that there's some even occupied vertices or odd occupied vertices, whether they're even or odd. But in a random graph is not bipartite. There's no even and odd vertices. There's no way to globally coordinate on like the way to make these boundary conditions work. And so somehow you can't see the same influence from the boundary that you see on the tree in this finite graph, even though it looks locally like the tree. So we shouldn't see lambda critical on the random regular graph. In fact, the phase transitions of the hardcore model on the random regular graph are very complicated, very interesting. I think we'll see from many points of view, both the probability and the algorithm's point of view. And I think we'll see much more about this later in the week. But I still want to come up with some finite graph where I see this phase transition. And so what can I do instead? I can say, well, let's consider a different random graph model. Now my random graph model is going to be a uniformly random delta regular bipartite graph. So I start with n being an even number, split my vertices into two equal pieces, and then join them, but all the edges cross. So now I do have even and odd vertices, I can call them. And I still get a locally tree-like graph. And so, right, so in terms of Benjamini-Schramm convergence, there's no difference between the random bipartite and the random regular graph. There's no difference. But we do have this possibility of global alignment. And so, in fact, there is a phase transition at lambda critical. And so what happens? If lambda is greater than lambda critical, so for lambda less than lambda critical, same thing happens. There's this unique Gibbs measure. It converges locally to the tree measure. Everything's nice. But for lambda greater than lambda critical, now we take a typical instance of this random graph, and then we pick an independent set from the hardcore model. It's either going to have more even vertices or more odd vertices by like a linear difference in the number of vertices. And a lot more, you can say a lot more. The fraction of even vertices and the fraction of odd vertices will correspond to the two extreme measures on the tree. So with 50-50 chance, you'll get basically the same fraction of even occupied that you get on the tree when you put this limiting even measure, or the same fraction you get if you put the limiting odd measure. And this is what we mean by phase coexistence. So if you sample from the model on the random graph, you'll see two sort of dramatically different configurations, one that has more even or one that has more odd. Sort of like the picture I showed on the right-hand side at the beginning. If I did the simulation again, you might see the same type of behavior, or you might see somehow the opposite. So this is phase coexistence on the random graph. But notice somehow the global structure of the random graph model really played an essential role here. Okay, good. So this is a good time to stop and ask for questions before the last section. So any questions about these different definitions of phase transitions, trees, random graphs? Yeah, so that would be one way to say it. Yeah, so either in terms of this like limiting free energy, there's a non-analytic point, or you could say in terms of correlation decay. Correlations fail to decay after lambda critical, because basically like once you condition on a vertex being n, you'll more likely be in the even dominated phase than the odd dominated phase, or vice versa. So in both those senses, yeah. Mm-hmm. Yeah, so that's a kind of tricky question, but yes. So I'm not sure how much of this is proved. Horace would know more, but just above lambda critical on the random regular graph that's not bipartite, I think like the covariance between two arbitrary vertices goes to 0, which is not true on the random bipartite graph. It would either be positive or negative, bounded away from 0. Yeah. On the tree or on the random bipartite graph. That's gonna, yeah. Yeah. So okay, so now I want to say, why are these type of phase transitions important? And they're important in algorithms. And so I want to tell you how the phase transition I just described on the random bipartite graph actually provides a link to computational complexity. And this is following the work of Sly in a really, really beautiful paper. So where do algorithms come in the first place? What algorithms are we talking about? So back to spin models on graphs, there's two very natural algorithmic problems. One is just I give you the graph and give you the specification of the model. Just produce a sample from the model. Like if you want to produce pretty pictures to give in your slides, you need to sample from the model. Okay, that's one computational problem. Another is to compute the partition function. The partition function has lots and lots of information. You might want to compute it. It generalizes, say, like counting from combinatorics. I will say that in general, computing the partition function is usually sharp p hard, which means it's as hard as exactly computing the number of satisfying assignments to a, say, 3-sat formula, really hard. And so instead, let's aim for like a very accurate multiplicative approximation, 1 plus or minus epsilon. So the two problems or the two goals for algorithms are to find an efficient approximate sampling algorithm. So given your graph, you want to output a random sample, so random independent set or a random plus minus 1 coloring in the Ising model case. And you want its distribution to be very close in total variation distance to the truth. Okay, and what running time do we allow you to make this efficient? Let's say polynomial in the size of the graph and 1 over the error parameter. So the more accurate you want this sample to be, you should pay more running time. What about approximating the partition function? So here we want to output a number, z hat, that's a 1 plus or minus epsilon multiplicative approximation to the partition function, again in time polynomial in the number of vertices and 1 over error parameter. If you have such an algorithm, it's called a FP-TAS, fully polynomial time approximation scheme. If you can do this with randomness, and let's say succeed with probably 2/3, then this is called an FP-RAS, fully polynomial time randomized approximation scheme. You know, one of the first and most famous results in this field is by Jerem and Sinclair. They said for the ferromagnetic Ising model, for any graph and any parameter beta, there's an efficient sampling algorithm in FP-RAS for the Ising model partition function. Okay. And it's based on fast mixing of a certain Markov chain, not the Glauber dynamics, not like somehow the natural change 1 spin Markov chain for the Ising model. That we know mixes slow on some graphs. Okay, so that's a computational problem. Now for hardcore, you certainly should not expect a Jerem Sinclair type theorem, right? Because if you pick large lambda, you're putting large weight on large probability mass on big independent sets. And actually finding large independent sets in a graph is a hard problem. It's not just NP hard to find the max independent set size, it's hard to approximate to like n to the 1 minus epsilon factor for any epsilon. So we definitely should not expect to be able to sample from the hardcore model on any graph at any lambda. But when can we? So that's the question. For which graphs and which lambda can we do these algorithmic problems efficiently? And so here is this result that I wanted to get to by the end. And this is due to Weitz, part of the theorem, Sly, another part, and then extending Sly's result to really cover all lambda above Sly and Sun and Galanis, Stepankovic, and Vagoda. But what this theorem says is, now remember lambda critical of delta, this is what we defined before. This is the phase, the uniqueness, non-uniqueness phase transition point of the hardcore model on this infinite graph, the infinite delta regular tree. Okay, so it's a phase transition in the uniqueness, non-uniqueness sense on one specific infinite graph, the regular tree. And what the theorem says is if lambda is less than this value of this critical value, then there are efficient algorithms for these problems for the hardcore model on the entire class of graphs of maximum degree delta. So look at all possible worst case graphs which have max degree at most delta, then you can do these problems efficiently if lambda is less than lambda critical. And the converse, I don't know, converse or whatever. The opposite is not is true or not true, however it goes. If lambda is greater than lambda critical, then no such algorithms exist for this class of graphs unless NP equals RP. So that means if you could solve NP hard problems in randomized polynomial time. So it's basically like saying it's NP hard. Okay, so this is kind of cool, right? Like you have a phase transition in the statistical physics sense, and it marks exactly a computational threshold when a certain very natural problem is tractable or intractable. Okay, so yeah, the phase transition, and I like to call it a computational threshold because the computational thing is not a phase transition in any of the definitions we use. It's a threshold, but the other one is really a phase transition in the sense that we define. And so in the last 3 minutes, I'll give you a really high level sketch of Sly's reduction. And so what did he show? So this is just the one side. This is the hardness side. Horace later today will tell you about Weitz, how you got the algorithm. But the hardness side, what he's going to show is if you can sample from this hardcore model on a max degree delta graph for lambda greater than lambda critical, then you can solve max cut on an arbitrary graph. So max cut, finding the cut that cuts the most edges in a graph. This is an NP hard problem. And so if you know that if you can sample, you can solve it, then, NP is NRP. Okay, so how does it go? You start with a graph H, and this is the graph where you want to solve the max cut problem. Okay. And we're going to construct a new graph where if you can sample, then you can find the max cut in this graph. And so as hardness proofs go, we're going to replace each vertex in this graph H by a gadget. Okay, and this gadget looks almost like a random delta regular bipartite graph. It basically is a random delta regular bipartite graph, except there's a sprinkling of a few vertices on each side that have degree delta minus 1 instead of delta. Okay. So those are the red vertices, and I'll call these like the connection vertices. And what we're going to do then is we're going to, replace each vertex in H by a gadget, and then join all the gadgets through their connection vertices, but keeping even joined to even and odd joined to odd. So if you see like the left guys are only getting joined to the left and the right guys are getting joined to the right, and we're only joining along pairs where there is an edge in H to start with. Notice that your gadgets were bipartite graphs, but if your big graph is not now a bipartite graph because you're joining even to even and odd to odd. Okay, and what Sly showed using first moment method, second moment method, small subgraph conditioning, fairly intricate technical work, was that the gadgets that are missing these things behave like random delta regular bipartite graphs. And then he showed some very precise behavior. In particular, if lambda is greater than lambda critical, they exhibit phase coexistence. Either you have more of the left guys in or more of the right. And in fact, these connection vertices, if you condition on the phase of the gadget, so if you have more evens or more odds, more left or more right, the joint distribution of these connection vertices is like a product measure, very close to a product measure, where the marginals are the right tree marginals. They're like the marginals you get on this infinite tree measure. And so you really have a very good understanding of their joint distribution. Now, you have a very good understanding of the joint distribution without the purple edges n of these red vertices. And now you can calculate, once you put the purple edges in, the effect of adding the purple edges. And that is a calculation, and the parameters have to work out so that somehow there's not too many purple edges that you destroy this phase coexistence property. And so you can show that. And then you use this very good understanding of the Gibbs measure and how these purple edges work to show that if you pick an independent set from the hardcore model on this blow-up graph with the gadgets, a few things happen. One thing that will happen is the vertices inside the gadget pieces will respect the phase. They won't all of a sudden do something crazy. The penalty you have to pay for violating this phase coexistence is huge. So you'll never see one that violates a phase. And if you go gadget by gadget and say, well, this is in the even phase, this is in the odd phase, this is even, odd, odd, and you put plus for even and minus for odd, then with very high probability, the pluses and minuses you see in this graph H, the one we started with, will exactly be a max cut of the graph. And so if you can sample from this model, then you just record which one, which phase each piece is in, and you get the max cut. And so therefore, if you can sample, and this graph is max degree delta, and so if you can sample from U, you can solve max cut. Okay, so let me just conclude by saying, okay, I showed, I talked about how computational thresholds can coincide with phase transitions on a tree. This is one reason trees play a really crucial role in the computer science perspective on this type of model. I'll say that hardness comes from using simple models as gadgets. In a lot of ways, the phase transition on the random bipartite graph is way simpler than the phase transitions on the random regular graph. And I'll talk tomorrow about like condensation threshold and cavity method and things like that. But the computational hardness comes from sort of the most simple models, the ones where we actually really understand the probability very well. But the gadgets themselves need not be hard instances. So, the gadget is a random bipartite graph. I could actually ask the algorithmic question on that. And there, you shouldn't necessarily expect it to be hard. And a great open question is, what about sampling from the hardcore model on a bipartite graph? Can you do that for all bipartite graphs and all lambda? The construction we just did, this H graph with the gadgets, is not bipartite. Okay. So actually, this is a big open question, and it's called sharp BIS, bipartite independent set. And that's unknown. We don't know. I'll also say that like these computational thresholds, they can be very hard to identify. So for a very natural model, just a uniform proper Q coloring of a graph, let's say a max degree delta graph, we still don't know what the computational threshold of this model is. But that's it. So thank you for your attention.
So you do the hardcore model on a graph which is bipartite, is like, I guess some ways easier to analyze. Have like this phase but you still expect sort of the non-trivial transitions for non-bipartite.
Yeah, but in a much more complicated way. So you'll see a couple of talks this week about this type of phase transition. But the nice thing about this random bipartite graph is somehow it's very easy to understand the phase transition because you just have phase coexistence between two phases, just two. But when you're looking at, let's say, independent sets, large independent sets in a random graph, not bipartite, there's somehow like exponentially many like local optima, it explodes. So it's like of a whole different character, where here you just have two.
What about a case where, so just going back to, well, I guess
yeah.
Right, that's not that well of a case, but just take a D2 and then add like all the know what that like.
So that was a big open problem for a long time, but I think Ron Peled and someone else just showed that phase transition exists, at least for very large lambda. But that's very, very recent. That's a great question. Yeah, that's a nice paper. Yeah. Yes, I think that's. Yes, that's right. That's right. Yeah. So Tom's exactly right. So like what happens when you put on this boundary condition that you're trying to get an interface depends a lot on dimension. Yeah, and 2 is very different than 3. Yeah. Thank you. Well.